Right, can you hear me?
Yes.
All right, good. Let's then start. How you doing?
Pretty good. How are you?
Good, good, thank you. And all right, so today's lecture. This is pretty much the last lecture in mechanics, and after that we will move on and study some other stuff. And so what I'm going to talk about today is importance of that mechanic, understanding of mechanics. On first of all, I want to really I don't know, make that impression. I don't know how to say it. I mean, put it in your mind that mechanics is actually much more interesting than what you might think about it. It's not just GT squared over 2 or that simple problems which we have in introductory classes, which actually just designed to be simple and very much detached from reality or from anything, in fact, interesting in this case, in this sense. Because we try when we teach that mechanics, we try to make it simple so that it's actually doable for when you just start on it. But it doesn't mean that's the point where you have to stop, right? You can continue, and it's a lot of very interesting stuff there. It's people still work on it, and there's still some discoveries made, and there are some problems which we still don't understand there. For example, chaos, how to describe chaos, how to describe turbulence in I don't know, hydrodynamics, and so forth. And those problems are actually quite important for everyday life. For example, the problems of turbulence, of how to describe the flow of liquids and gases is extremely important because it's pretty much all engines which we have in cars will benefit a lot if we actually understood how they work. Right now, we have only empirical knowledge, and there is no real good way to describe it. A lot of is known, a lot of it understood, but there are a lot of things which we actually don't even know how to describe. So that's one reason for mechanics. What I'm trying to do. And the other thing is that what we learn from mechanics, we actually use it all the time. It's well, first of all devices which we use for measurement, right? So when you do some measurement, and by measurement I mean pretty much anything you do to a system, right? Remember that measurement doesn't require you to have a big laboratory or something like that. When you're using your iPhone and whatever smartphone you use, and then go to I don't know, Twitter, whatever. It's what you're actually doing from scientific perspective, right? Not from entertainment industry, but from scientific perspective. What you're doing is a bunch of experiments on measurements, and in fact, on and majority of them are quantum mechanical. So you're actually doing some quantum mechanical measurements, but your device is always classical. So we cannot have quantum device. The output of any measurement is always some number, right? Real number, and so it's always classical measurement. So at the end of the day, no matter what happens in a system, what we see about it is some sort of classical, I don't know, classical values, classical understanding, right? So in this sense, it's the last, and no matter what you do, the last part of any experiment, in very broad sense, experiment is always a classical, some classical measurement. So in this sense, how classical system behave is very important for pretty much anything we do. That's one thing, but another thing is that we actually learn a lot from classical mechanics. Like remember what I told you that when you leave any system alone, it will eventually come to equilibrium. That eventually doesn't mean long time. In majority of in many cases, it's actually a time which we cannot even observe. It's so short. So it will come to equilibrium, right? And close to equilibrium, everything is can be described as a set of harmonic oscillators. Simply because equilibrium is a minimum of potential energy, and any function which is close to its minimum can be described as a quadratic potential, and the quadratic potential is oscillating. So what we have typically we start with is some sort of oscillator, right? And it's an equilibrium. Now, we don't observe that. What we can observe, we can only observe responses. We can do something to system and see how it responds to us, right? So to our actions. Those are called responses. So when the system close to equilibrium, what we have is a response of a bunch of oscillators, right? Doesn't matter what action we do. I mean, it can be sound waves, like, I don't know, electromagnetic waves, like light, microwaves, also like whatever. It's still a response of a bunch of oscillators. And that's our basis of understanding what's going on. So and now we know what will happen there, right? Because it's any oscillator will have some resonance frequency, maybe many of them, many resonance frequencies, right? So we can tune our action in the same frequency, the resonance frequency, right, and observe the resonance, right? We can shift out with the frequency of what we do, like electromagnetic waves, light, and see how response is changing as function of frequency. Because there is a resonance, there will be some peaks in absorption or whatever response we measure. And so that peak is telling us what is the resonance frequency of that particular system. And after that, what we can do is to take those resonance frequency, right, and try to compute it try to make a hypothesis of what's going on in the system, which gives us that resonance frequency. So we can, well, it's some sort of oscillator, so we can figure out what exactly the shape of that potential is, right? And after that, we already know something about the system. But we can do even better than that, because the resonance will always have width. And that width, if your instrument is precise enough, right, that the width is internal width of that resonance. And that width is given by dissipation in the system. I didn't have time to explain that, but it's written in my lectures, and you're supposed to know that that the width of the resonance is connected to, is given by dissipation in the system. Now, dissipation in the system means that our oscillator is coupled to something big, some large subsystem which can absorb energy and never give it back. All right. So by measuring, then studying how the width of the resonance is changing as function of, I don't know, temperature, magnetic field, frequency, whatever, we can actually learn something about that other system which our resonator is coupled to. So after we understood the resonator, we can actually the oscillators, we can actually use that knowledge to study something which we actually don't know, right? Coupling to some other system, and so we can learn something about that coupling to some other system, and we can now make a hypothesis about that some other system, and then see how it works, and see if we can predict the behavior which we measure, or make even better, make some other invent some other experiments which would show that our hypothesis is correct, and so forth. So using something which we already know, which we learned before on the previous step, we can use it to learn the next step and next and so forth. So we can increase our knowledge on systems. Now let me give you an example of that. You all heard about MRI, right? It's MRI machines in hospitals which like measure your brain or whatever they measure. Right? Now, MRI stands for magnetic resonance imaging. It first appeared, that device first appeared as a physics laboratories as a device to measure some physical properties, and it was called NMR, nuclear magnetic resonance. Now, those health people don't want to use the word nuclear for their devices, so they change the name to MRI. But in reality, it's NMR, nuclear magnetic resonance. And what it measures is the resonance frequency of nuclears. Nuclears do have spin, and it means that they do have magnetic moments. So when you put them in magnetic field and then excite it with some other magnetic field with different directions, you can see that exactly that resonance effect. It's actually exactly the same as what you study in classical mechanics. It is quantum, but it actually makes it somewhat simpler. And so that resonance frequency tells you what kind of nuclears where and where they are. So we can actually figure out where different nuclears of different elements are inside your brain, and then map that to a picture. And that's exactly what MRI is doing. But we can do better, because as normal resonance, that nuclear magnetic resonance will have width, right? And that width means that the nuclears are coupled to something else. There is some other subsystem, huge subsystems, which this particular nuclear is coupled. There are a few such things in normal I don't know, bodies, or I mean body, not like human body, but human body also. It's something like, well, sound waves, right? The oscillations of the nuclears, they are like, if you consider crystals, they, because of the temperature, for example, they oscillate a little bit, and that changes. And it means that whatever I change with one nuclear will propagate away to some other nuclears, that's exactly the coupling of that nuclear to the rest of the system. That's one way to have dissipation. The other way to have dissipation is actually more interesting in some sense. Well, for me at least, it's the fact that nuclear spin, that nuclear magnetic moment, is coupled to electrons also. Electrons also have magnetic moment. So when a nucleus changes its magnetic moment, it's actually changes the magnetic moments of the electrons around it. And then those electrons, especially if they are in metal, they will that disturbance of electronic liquid actually inside the metal actually propagates away, and that's what gives you dissipation for a nuclear. So by studying that the width of that resonance, you actually learn something about how electrons behave in the metal, right? And it turns out that it's incredibly powerful tool, and a lot of people do that. And in particular in this building, well, not in this building, we have a laboratory in the next building where people actually do exactly that nuclear magnetic resonance for different materials, studying electronic properties of those materials using the nuclear magnetic resonance, using the width. Now, there are a bunch of techniques there which it tells you that if you switch like magnetic fields in some specific particular way, there is some experiments which tell you that there are some effects which is called spin echo, and it actually allows you to measure something else about electrons and so forth. So when we try to describe the behavior of electrons in the material, we can actually use that NMR as one of the tools. There are a bunch of other tools like conductivity, measuring conductivity, Hall effect, and all of them. But NMR is one of them, and it's actually directly connected to the properties of the resonance in typical oscillators. And we then can see how behavior of electron changes when we change temperature. And for example, when we go through superconducting transition and metals become superconductor, then it's actually quite visible in NMR. It's one of the best tools in this sense. And there are plenty other things which we can do there. And in particular, that width will be very different depending on whether you have a metal or insulator or semiconductor and so forth. So all of that things can be used, and then we can study the properties of the materials, electronic properties of the materials in more detail than just like measuring some transport like current and resistivity and so forth. So it's one of the one of those tools which allows you to look at, and it's actually very versatile tool because you also can have magnetic resonance different in different parts of the material. So if you have some homogeneity there, you can study it and so forth. So there are plenty of techniques of what you can do in this situation, what you can learn about the material, and so which we can use to learn a lot about that material. Now, after we learn a lot about some material, we can think about how to use it, right? And typically it means that we need to connect a couple of materials and make a small device out of it. And then that small device can be used like in the big devices and to provide some properties which we need. For example, your smartphone. And plenty other things. But in fact, majority of what things which you use are the properties of some specific properties, very specific properties of some very specific materials which were studied first in the laboratories, and then the people figure out, and engineers and scientists they figure out how to put things together to make the device which you need, and then so maybe you don't need, maybe you don't know that you need it. All right, so that's again, that's all understanding comes from understanding of simple mechanical resonances, and but there are plenty other effects which also exist in classical mechanics, and we also use them, and some of them we actually really want to use. And a lot of research right now is coupled to is about how to use some of those things which we know from mechanics, in fact, and which actually exist in mechanics, and to make some new devices which are more robust, cheaper, whatever, faster, you name it. So let's think about it. What we can do, and today I want to talk about those effects, not the resonances. But think what we can, what else can we do with the oscillator? When we consider oscillator, what we did is we said that, well, typical oscillator is described by this equation, right? Well, this is an oscillator equation. This is the simplest one. Well, that's the essence of it. If you have many coupled oscillators, then actually it's possible to rename your variables in such a way that they become decoupled, and each of them is described by this equation. It's just the meaning of that x is changing, but the meaning of that x also depends on what kind of problems you consider. And for example, if it's LC circuit, then this is a charge of a capacitor, right? And so forth. If it's normal spring with mass, then this is position. If it's pendulum, it's angle, and so forth. So there's a meaning of that variables can change quite, depends on what you have, what system you consider. But the equation will always be the same, and that's the power of math, right? You can have many different situations, but they all described by the same equation. So we studying that equation, we already know a lot about different systems. We just need to reinterpret our results in a new, for each new system, just looking at what kind of variables we use. All right. So, but now let's consider the following situation. I was considering that omega not to be a constant, right? So it's some property of my my system. But I can also think about it that it's something which I can control. For example, in LC circuit, right? That's 1 over omega is 1 over square root of LC. And so what you have then is capacitor times inductance, and both of them you can change by hand. So you can have variable capacitor or inductor, and you can change them as function of time, right? It's in your hands. So what I want to consider now, I want to consider the situation. I want to consider that omega to be a function of time. So that parameter depends on time. The parameter of the frequency. So for example, if you have a pendulum, right, then I can imagine that what I do is I change the length L of the pendulum as function of time. Right? It's my pendulum. I can do whatever I want with it. So I can, for example, pull it up and down from if it's a rope, right? I can pull it up and down a little bit, so that the length is changing of the pendulum. And if length of the pendulum is changing, that omega naught is changing as function of time. Or if it's LC circuit, I can imagine that my either conductor or capacitor are driven by some other system which actually changing its capacitors or capacitance or inductance, and so forth. So then it's that's the equation which I have with this one, right? That makes sense.
Yeah.
So that's kind of problems which I want to consider when this omega is function of time. Now, if you think about it and think about this simply as an equation, and then what you have is now is completely different equation, right? Because now you have dependence on time also here. So if you look for the solution in our standard form, it will not work anymore. So let me use it here. Right? It will not work anymore because remember that simple story worked before, because when I substituted that kind of solution instead of x or whatever variable I use, right? Then because of that exponent is such a simple function, all differentiations just put I omega in front of that. Right? The all time dependence are in the same factor, e to I omega t, and that time dependence cancels out of this equation in this case. And because it cancels, then after that I have just an algebraic equation for that parameter capital omega, and I can solve it, and then whether I have dissipation or not, I can solve it, and that's exactly what gives me the frequency of my oscillation. But now it will not happen, because yes, if I substitute it here, that factor will cancel, but I still have dependence on time. And what I will have then is some algebraic equation which doesn't have a solution. And if you try to be clever and say that this depends on time, then when you differentiate that exponent, you also have to differentiate this function, right? It becomes by chain rule. And then instead of this equation, you will have another differential equation for the now function omega of t. And in fact, that differential equation will be more complicated than this. So that same solution doesn't work anymore. That system behaves completely differently. And that's so. In this sense, it doesn't really make sense to talk about that equation in general, because the solution will very much depend on the form of the function omega squared of t. That makes sense? Do you understand that it's a completely different story now? You don't have a solution to this equation. You definitely don't have a general solution for arbitrary function omega square of t. And if it is not arbitrary function, if it's something else, like for example, if it's linear in t, then in fact, what you will have is a solution which are called airy functions, and those are special functions which you can study if you want, and so forth. So there are plenty of that equation can be solved, and there are solutions, and they were studied a lot. Those solutions for some specific forms of that function omega square of t. But remember that it's your parameter; it's in your hands, so you don't have to be very specific. You can do whatever you want, right, with that. So what do we do now? Well, of course, for any specific form of that function, we can just solve that equation numerically. That's possible. We need to set up some initial conditions and just run it through numerical packets and get the solution. Right? Is it clear?
Professor?
Yeah.
Is it possible if you could provide like examples in which, you know, you're using the same formula, so we can have a better understanding of when to use the formula?
So that's exactly what I'm saying. You cannot, right? So the solution of this equation very much depends on the form of this function. So, and pretty much for any form of this function, the solution will be some sort of special function. Even if it's that just a linear function of t, the solution is Airy function, right? So that I just solved it for you. Do you know what Airy functions are?
Yeah.
Well, trust me, I don't know either.
Yeah.
Well, I do know a little bit about them, but, because I had them, but that's about it. Right? So it becomes very complicated equation. As soon as that this is not constant, the solution becomes very complicated. Right? And it's in fact so complicated that it really doesn't make sense to work on it unless you actually really have to, for example, for your thesis, right, or whatever, for some engineering problem. But then if you have some specific form of this function, then it's actually easier to solve it in initial conditions. Then it's easier to solve it numerically. Okay, and I cannot do numerical solution on Blackboard. Sorry.
All right. Thank you.
Right. So then what we do in this situation? What we do, we want to think about what we actually want from it. Right. Right now, I just told you that, well, if you have this equation, depending on that function, you can do whatever you can get whatever you want, really. And but let me think about it the following way. Let me think that it is still an oscillator. I don't want to go too far away from something which I already know quite well, an oscillator. I want to say that this is still an oscillator, right? And in order to do that, what I will demand is that that function omega squared of t, and there is some constant which is omega naught squared, right? And this function actually changes just a little bit around here. So it's never too large, it's never too small. It's just like sort of like changing a little bit around some specific value. In this sense, I can think about it the first sort of approximation. I can think that this is just a constant, and then there is a small changes on top of the oscillator. So I never really go too far from an oscillator. I don't want it, because it's if I do that, my solution change very considerably, and it's completely different problem. I still want to think about it as an oscillator, and that parameter depends on time very weakly. That makes sense? So in particular, if you have one of the examples which you're actually quite familiar with, if I have a pendulum, right, and I change its length, but I don't change it a lot, I change it just a little bit. Okay, so let's say that the length here is L, our acceleration of free fall is G, then the frequency the frequency of this oscillator omega naught squared equals G divided by L. Right? You know this, right? Right?
Yes.
But now imagine that I change that length just a little bit as function of time. Have you seen such situation? Come on, tell me. That was a question for you. Have you seen a situation when you have a pendulum and you change in its length just a little bit? Around?
No.
No? Have you ever been on a swing? You know the swing, like,
Yes.
that's what you do, right? On a swing, you stay, well, let me, in one particular situation, you stay here, right? And you bend your knees up and down. So your center of mass is going up and down, right? And that, but that's exactly the change of the length of the pendulum. That makes sense?
Yeah.
Wait,
Yes. Yeah.
I'm confused. You said you're swinging your knees changing. Can you say it again, please?
When you're swinging, standing up, right, on the swing, what do you do in order to keep swinging?
You're changing your center of mass.
You bend your knees, right, up and down.
Yeah.
So your center of mass is moving.
Yeah.
Right. So, but that length is actually the length to the center of mass, total center of mass. So you're changing your own center of mass up and down. Then it means that L is changing a little bit.
Oh yeah.
It doesn't change much, right? You never. It's just changing just a bit.
Oh, okay.
So that's exactly what I'm describing here. So that from the point of view of this equation, what happens is that now this function is function of time, right? Which you provided this function of time. You go, you bending your knees up and down, and then, so you change this little L by just a little bit, right? So this is L naught. So now this function is some L naught initial value plus some delta L, which is function of time. This is your knees, right? Which you put up and down. And after that, if you want, and this is much smaller than this one, so you can use Taylor expansion for this function, and then what we see is just omega squared is changing a little bit, but it's actually seen from here, even without Taylor. Right? So that's one thing. I don't want to change this too much, right? But then the only choice I have pretty much is either my omega squared t goes from one constant to another constant, right? But and that, so I either have this situation when I start from here and then I go like something like this, and it's because I cannot change it much, right? I have to be around it, or I can do it periodically, and that's exactly what I want to consider. I want to consider a situation when you have that omega as function of omega squared as function of t is changing periodically. Okay, so it never goes too much away from that average value. So this is my omega naught, and this is much smaller than omega naught, right? So it's always staying pretty much the same, but changing with time. And the period of that change, again, it's my function. I can do whatever I want. So I can. This is time, right? And so here's the period of that change, right? Does that make sense?
Yes.
So I change it periodically, but if I have a period of the change, I can say that I have a frequency of change. So I have omega p, and by the way, this p is staying for pumping for me, and because that's typical situation, you pump the system with something, and which is just 2 pi divided by that period. It's a frequency of the change of the frequency. Does that make sense?
Yeah.
And now I can consider different situations. Remember that this is still the amplitude of the change. It's very small. But I can consider 3 different situations. I can consider a situation when omega naught is much larger than omega p. So that change is really slow in comparison to the typical change, to the typical motion of oscillator. So oscillator changes fast, like it oscillates fast, and I slowly change the parameters of this oscillator. That makes sense?
Yeah.
Now that's the first case. The second case is the opposite. Then omega naught is much smaller than omega pumpkin. And what it means is that I have oscillator which oscillate, right, very slowly, and I change its parameters very, very fast. So I have a pendulum which swings around slowly, and I change the parameters very, 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 very fast. And the third case is, of course, when they are of the same order. So omega naught is of the same order of omega t. Right? So I can consider those three different cases and try to find out whether I can find something in those cases which I can use, which are interesting, don't depend on the details, and they can be used in some other thing. Is it clear?
Yeah.
So it's called the oscillations with parameter depending on time. Parameters depending on time. So that's my function. And if you think about it, that's exactly, I mean, in many cases, that's exactly what's happening. For example, when you have a metal, right, and you put a sound wave through it, and you're interested in what's going on with electrons. So that sound wave is changing the position of crystal nucleus, and the electrons somehow need to respond to it. So they're sort of oscillator, and we change the parameters of those oscillators, and so forth. So there are plenty of other situations when it is when it's exactly that case. So now let's consider the first one, when parameters are changing very, very, very slowly. So it means that during that change, during one period of change of the frequency, that oscillator can oscillate many, many, many times. Okay. All right. So in this particular case, when I have just one-dimensional oscillator, that's actually not very interesting problem. It becomes very interesting when I add one more degree of freedom to the oscillator. And that's what I'm going to do. And consider a very simple situation. I won't consider pendulum. So it's a pendulum. We know that it swings, right? Up and down. That's my oscillator. Does it make sense?
Yes.
Yep.
But now I want to say that this point actually does not restrict that the pendulum to be in this plane. It can also oscillate in a plane which goes perpendicular to the plane, right? Or whatever other end.
So it could slide.
Well, it can rotate like this, spin like this.
Oh, okay.
It will move like this. No, it cannot slide. The point is attached, but it can oscillate on any plane.
Gotcha. Okay.
Right. So it means that that point has actually 2 degrees of freedom. One is phi, and the other, well, it's this angle. Let's call it psi. So it also can swing. But now what I want to do, I want to start the oscillations just in one plane and see what happens. So my initial conditions are such that psi doesn't change, right? And it's oscillates just in plane. Do you know what will happen? Have you seen such pendulum?
Yeah. Sometimes it kind of go. There's the one in the mist building, right?
Exactly. Yes, it's called Foucault pendulum, right? That's correct. So what will happen? What is the parameter here which I want to change? Now it's a tricky story. Remember that we are on Earth, right? Right? We are on Earth. I'm not sure where you are, but I am here. So we sit in somewhere here. Here is our pendulum. And now, and the Earth is actually spinning. You know that, right? That's why we have day, night. So it spins around its axis, and this is North Pole. This is South Pole, and it's spinning And so we are spinning, right? So we are sitting on Earth, and the Earth is spinning. So we are not in the inertial frame of reference, right? We are going around the circle.
Yeah.
That doesn't. That, by the way, is the reason why we have, for example, Coriolis force or centrifugal force and Coriolis force. You know, when we observe something on Earth. But in many cases, that can be ignored because it's the time you do an experiment is not long enough to actually see the rotation of Earth. But now that's exactly what it is, right? It's the rotation of Earth is much slower than the motion of this pendulum. This pendulum oscillates many times, while Earth is just making one way around, which is exactly 24 hours, right? So if my period of my oscillations is much smaller than 24 hours, then I have exactly this situation. But now, what is the parameter? The parameter which changes is the direction of the acceleration of free fall. You see that's exactly what I think people have problems with in this situation. So the acceleration of free fall is perpendicular to surface. It's like this, right? Right?
Yeah.
Yes.
So you see that in this place it is here, on this place it is here. This is direction, right? So direction is actually changing. It is not changing for you when you're sitting here, but remember that you are not in the inertial frame of reference. In order to see that, you need to imagine yourself to be in inertial frame of reference, outside of Earth. And if you're outside of Earth, what you see is that pendulum, that acceleration of free fall is changing direction. That makes sense?
Yeah.
Uh-huh.
All right. So, any questions? So if you in this sense, when I try to, but I need to write everything in the inertial frame of references, or think about it in inertial frame of reference. If I do that, I have to say that my vector of g, I can consider it to be constant in magnitude, but it's actually changing in time its direction. It's going like this, right? And then I need to consider a pendulum which has that g changing with time. So that g is actually changing with time. It's a time dependent. It's not. Its direction is changing with time. And that's exactly motion of my parameter. Now that direction of g, of course, returns back after 24 hours. So in this particular case, that period is 24 hours, and the period of oscillations is much smaller. So the frequency of oscillation is much larger than the frequency of the change of the of parameter. And so this is this case. Okay? That makes sense?
Yeah.
All right. Now, in our non-inertial frame of references, that the effect which I'm going to describe can be attributed to Coriolis force. But if you are outside of and you try to describe it in the inertial frame of references, there is no such thing as Coriolis force, and then it's just the effect of that rotation of g. So the explanation depends on what frame of reference you want to consider. And now, what actually happens in this situation? And I'm not going to derive that. I'm not going to derive anything today. But I just tell you the result. Then, when this pendulum goes all the way around and returns back, right? That delta psi, this psi, the angle which the plane of pendulum is making, right, equals minus 2 pi sine theta, where theta is exactly our position. That angle. Okay? Does that make sense?
Wait, why is it negative?
Well, first of all, it very much, whether it's negative or positive, depends what is the direction of my sine. Right?
Oh, okay. So it's just accounting for if it
Yeah,
being okay.
So I think it's exactly for this picture it is negative. I might be wrong, but it really doesn't matter. I mean, it depends on how you count. So what it means is the following: that if you now observe you are in a tower, right? Imagine that like you're in the 7th floor of our building. You cannot go there, but it's low. But anyway, if you're there and you're looking at the pendulum, down at the pendulum, right? Then what you see is the pendulum which is oscillating back and forth, right? You're looking from top of it, and what you see is that bob is going back and forth like this, right? Now, if you're patient enough and you observe it for 24 hours, when the pendulum returns back to where it was, right? Not in your frame of references, but in the inertial frame of reference, it returns back to where it was when it made the full loop on the surface of the sphere. Then what you will have is that, so this is your oscillation back and forth. What you will have is oscillations which are now on different planes, like this. And this angle between those two planes will depend on where you are. Right? If you are in different places of Earth, that angle will be different. You can actually use that angle to measure your latitude. Okay? That makes sense?
Yes.
All right, so that's the result. I mean, there's no derivation here. I can derive it and actually do in my other classes. So if you take it, I'll show it how it's done. But again, it's a standard situation. You write Lagrangian and then so forth. And but that's the result. Now that result is very, very interesting. Let's look at that and notice the following thing: that our pendulum, when you're looking from outside of Earth, it's going around the loop, right? That makes sense?
Yeah.
Now let's take this area of Earth within this loop. Just measure the area. So this is area. And let's now take this area. Remember that area has units meter squared, kilometer squared, whatever you mean, and divide it by the radius of the Earth squared. Okay. So now it's dimensionless number, and that number is this one. Maybe plus 2 pi. It's really not that important because angle of 2 pi is not measurable. So it's that quantity is actually called the solid angle of in the spherical geometries. It has special name, but it's nevertheless purely geometrical quantity. It just depends on what area the path is enclosing. Okay, does that make sense?
Yeah.
So now it's actually becomes completely geometrical story. If you just imagine that our Earth is not rotating, not spinning. Okay, it's not our Earth, but whatever, it's not spinning. And we do this experiment, but now we have the pendulum, and it's not moving anywhere. But now instead of pendulum and move it around ourselves and come back. So we take this pendulum and just move around over some closed loop and come back. Right? Then exactly the same thing will happen. And if you start the pendulum oscillating stays this direction, then when we return back, it will be oscillating in this plane. Okay? And this angle of rotation of that plane of oscillations when you return back, right? That it equals to this area inside this loop, the area first, divided by the radius of Earth square. It's again exactly the same result. Right? That makes sense? Now, let me point out one subtle thing here. You cannot measure the angle, this angle of the plane between two different points. Right? That's curved geometry. You don't have parallel lines. That quantity will depend how you measure, how you define your angle. All right? But you can measure that when you return back exactly at this point where you started, because now you measure an angle. You can basically draw a line on the sand, right, where your plane of oscillation was, and then when you go all the way around and come back, you can measure the plane of oscillations with respect to the same line on the sand. That you can do, and so, but that requires that path to always be closed path. So that quantity of rotation of that of the plane of oscillation only can be defined unambiguously for closed path. Right? And then you can use that that expression of a solid angle of area divided by radius squared, and that will be the result. So in this sense, and by the way, that result does not depend how fast you go. If you go slow enough, and if you go fast enough, we will change this requirement. But if you slow enough, so that requirement still holds, then the result does not depend on how fast you go. Okay, you can double your speed. If its speed is very small, you can double your speed. It still will be the same result. So it completely doesn't depend on how you move that that pendulum around. The result is very, very universal. Okay, does that make sense?
Yes.
All right. So that's Foucault pendulum, and it's actually the fact that Foucault pendulum changes that plane of oscillations. The plane of oscillations rotating is, of course, has been known to Foucault and to like 200-300 years ago, and but the fact that it's very, very geometrical result, although the result was known, but the fact that it's very geometrical property, it depends only on geometry of things. It's has been basically, again, let me say that solid angle is exactly the same solid angle which that vector G is making. Right? So it's basically completely. It doesn't even require Earth. You can do it anywhere. Just for example, if you are in weightless space, but this is charged particle, and you put it inside a capacitor, and then you just sort of move the capacitor around. It will be exactly the same. So it's slowly move the capacitor. So that's that fact that it's very, very geometrical. The result has been recognized only in 80s of last century, 1984. Right? And moreover, it was not recognized in classical mechanics. It was first recognized in quantum mechanics, and only by Michael Berry. And then it was people just took it and moved it to classical mechanics. It took about 1 year. So in classical mechanics, the same concept appeared in 1985. Now, 1985, 1984, I was already quite alive. I was a teenager. So it's very kind of new way of looking at things. And although the results were known before, but the fact, the universality of that result was not really completely understood. And after Michael Berry actually made that explanation that it's absolutely geometrical property, and it's now in quantum mechanics. This is the whole area of results of that kind is called Berry phase. And that's actually what people want to use a lot, simply because that does not depend on detail. That effects do not depend on details. So you don't really need to have very good control over your device, and it means you can manufacture it much cheaper, much cheaper, right? You don't need to be very, very precise there. And but the result will still be the same because it cannot be changed. It's geometry, right? So what we a lot of us are trying to do right now is to find out how we can use those things in order to do computations, memory devices, and so forth, because then they don't depend on details, and we can do it cheaper. They will be more robust, and so forth, so on. So that's quite that effect is very phase in quantum mechanics is one of the most important effects right now, and it was discovered recently. Well, for you it maybe not recently, but I remember those times. So it's so that results the fact that it's universal and very robust and geometrical means that we can do some interesting stuff cheaply. That make any sense?
Yes.
All right. Okay, so that's this example. Now let's move to the next one. And there's the opposite one. Here, the parameters were changing very, very slowly. And it's called, by the way, sometimes adiabatic approximation. When we change parameters very slowly. And now we have the opposite situation, and this one. Now that's the difference, a completely different story. Now it means that my function is changing. My function omega square root of t is changing much faster than the oscillations themselves. So when I look at the oscillations, one oscillation is taking some time, right? And during that time of one oscillation, my parameter changes many times. Okay. All right. Okay. So that, in fact, because it's a linear equation, if I just do it in this equation and try to find something interesting, nothing interesting will come up. It's because it's of the linearity of this equation. But if I add some non-linearity to this equation, for example, if I don't consider the oscillator itself, but instead I consider pendulum. Remember, pendulum is actually non-linear, right? What you have there is phi double dot equals minus g divided by L times sine phi, right? So when phi is very small, I can say that instead of some phi, I can write just phi. But in reality, it has corrections, right? So the next correction will be phi to the third, and so forth. It's called Taylor expansion. So there is built-in nonlinearity in that, and that if I use Taylor expansion here, right? So I write phi. That's the first part of the Taylor expansion, and second is 1 over 3 factorial phi to the cube. Right? That's the next term in the Taylor expansion. So you see that this is linear. This is linear, right? This is phi just in first power, but this is phi to the third power. So it's non-linear term, and that this non-linear term is actually quite important for what I'm going to say. That non-linearity allows us to actually couple that is very, very fast oscillations to the of the parameter to the oscillation of oscillator itself. Okay, again, if you want to know details, how to compute, how to use that that condition in equations, welcome to my class next year. I'll explain there, but here I'll show you just the result. And so what we have, how do we construct that? Let's do it very, very simply. Let's say that we have an oscillator, a pendulum. Right? But now what I want to do, I want to take this pivot point. I think that's how it's called. Right? This is my ball. It's just a story, and I want to shake it up and down. Just take it and then just shake it. So that position of that pivot point is given by some function. Let's call it psi of p. And that function is periodic. I shake it up and down, and I shake it very, very fast. And amplitude of this shaking is very small. So that amplitude is very small. In fact, all of those conditions can be combined together. And if I remember it correctly, that psi dot squared average. Let me look at it. Yeah. Must be much larger than G times L. G is my acceleration of free fall, and L is the length of this pendulum. This is an exact condition which I can use actually to solve this problem. And again, if you take the analytical mechanics class, I'll show you there. The calculation is quite involved. I don't want to do that, and but I give you the answer, right? And I don't even give you the answer. I actually show you because I have a device exactly like that, right here. And so, do you understand the device? I mean, do you understand what I do? I just take a pendulum, right, and I shake that point where it's hanging, up and down. Do you understand it? Any questions about it?
No.
No, sir.
All right, I'm going to show you that device, and this is the device. Can you see it? It's made out of Lego. One of the students made it.
Yeah.
Can you see it?
Yeah.
Yeah, that's good.
Yes, sir.
Yeah. So this is a pendulum. See that little piece?
Uh-huh.
And it has that crank here, and if I turn it, you see that it's going up and down.
Okay.
Right? So the situation which I described, it's like this one, right? It's going up and down. You see it?
Yes.
Yes.
Okay. So right now I was moving it very slowly, and now I want to do it fast, and I'm not sure that I need to set it on something, otherwise because my hands are not steady enough. And so let me try to show it. I need to move my camera for that. Can you see it? Let me move it probably better. Can you see it right now?
Yes, sir.
Is it visible?
Yes.
Now let me move it quicker. Do you see it?
Yes. Yeah.
Do you see that it slides actually up on top?
Yeah.
Yeah.
All right. Let me now come back. So this is quite a surprising result, right?
Yeah.
It's a little completely unnatural. Really, trust me. I've shown it to many professional physicists, and everyone is completely amazed. I mean, because for some reason it's not known very widely in physics community, except in Russian community, because in Russian it's called Kapitsa pendulum. Kapitsa is the name of the guy who actually invented the story, and it's just simple like that. If you shake it fast enough, then the pendulum is actually going. The pendulum acquires another equilibrium position. Now that device is made such a way that it goes up. It actually hits the foundation of it and goes up. The point down here, this oscillations are also always stable equilibrium. But if I shake it fast enough, another stable equilibrium appears, and it's up top. And then if I take my pendulum and move it up here, it will start to oscillate around the top point. Okay? If I shake it fast enough. So it can oscillate down there. It doesn't do in my device just simply because it's designed such a way as to move that pendulum up there. Simply because I don't have the third hand. I need to hold the device in one hand, rotate it in another, and I need third hand to actually move it up. So it was the student who made that it designed in such a way that it moves up. But nevertheless, that if you shake it fast enough, is that quantity, that average of psi dot square. Right? If it's fast enough, if it's large enough, much larger than GL, then it actually the new stable point appears and the oscillator starts to move like this. Acquires a new stable point. Okay, that makes sense. So I found it's completely like marvelous thing, and it's actually doable. You can like you write Lagrangian for the system, you write Lagrangian equations, and then the trick is how to use this condition in order to find out what's going on there, how to basically average over the small shaking. And after you've done this average correctly, you actually find that's indeed effective potential energy requires additional minimum there. So I'm not gonna do that. It takes quite a long lecture, and the calculation is quite involved. But nevertheless, again, it's doable. It's not a big deal. But I want to point out in one simple thing. That device is not very fast, right? I'm just looking at it, and if you make it a little bit more faster, Lego will break down. But that you see that the only condition which I have that quantity psi dot squared is small, is large, right? So psi by itself, the amplitude can be very small, but the shaking must be very fast, right? So that you see that the psi dot is the velocity, right? And what's written here is basically velocity squared and average, right? It's changing with time, so I need to average over some time, and that's exactly what the quantity. So the only thing which I need is large velocity, but large velocity doesn't mean large amplitude. I can shake it very fast, but very little. Right? That makes sense?
Uh-huh.
But if I do it this way, right, you will not actually see that I'm shaking it. I can shake it so fast that your eyes will not register that motion. I shake it fast and very small, right, amplitude. So your eyes will not register this motion. But that new thing on up top will still appear. So for any observer, it will look like anti-gravity. Right? The gravity changes direction, and that pendulum starts to oscillate up top. Okay, so it can be done in very I don't know, confusing way. All right, so with this device which I have, you actually see that it's moving up and down, but it doesn't have to be so. We can make a device which you cannot see, and then it will still behave the same way. So it's basically in one point I was told it once that it gave a huge problem because it does look like gravity. In fact. So your potential energy just changes its form, but all you know is potential energy. So it looks from everything as if gravity changes form, changes sign. So when they once they built a scientific laboratories in MKS, International Space Station. So in space stations, they built that laboratory which was designed to do some zero gravity experiments. Right? And but the laboratory there's some air needs to be pumped up there, right? Because the laboratory, we need to breathe. And so they didn't think about it much, and they attached that engine which was moving air to the laboratory itself. So the laboratory starts to vibrate just a little bit, but very fast. Right? So all the experiments were screwed up because for all experiments that looks like gravity because of the same. So that's one thing. And another thing which is also very interesting and also known to very, very few physicists, surprisingly few. So I was shaking up and down, right? So what will happen if I shake it horizontally? Well, I can do that experiment also here. All I need to do is to rotate it like that and shake. And now you can see it actually. Can you see it? What happens?
Yes.
So in fact, it's if I shake it fast enough, but again, it can be very small, but I shake it fast enough, then what happens is that the pendulum acquires new two stable minima, and this minimum down there becomes unstable, right? So if I take this phi, what and write the effective potential energy after averaging effective potential energy, it looks like this. Have you seen it before?
Yes.
Yes, it was last lecture, right? It's a spontaneous symmetry breaking, and it's exactly what is happening. So if I shake it, and if I don't shake it fast enough, then of course this is a stable minimum, and then all I have is just this standard potential energy, right? But if I start shaking fast enough and I average over that fast motion, and I look only on the slow motion of the pendulum, then what happens is that two new minima at fast enough shaking, those two new minima appears, and they behave exactly the same as I described last lecture. It's exactly the same. It's quite amazing that how universal that picture which I described last lecture. So again, it describes like squared phi to the squared term, then phi to the fourth term, and the coefficient in front of the phi to the squared changes sign. And that's when the transition happens. Moreover, that happens. You see that in this particular case, that situation happens because I have two different motions in a system. I have very fast motion and very slow. And that fast motion, right, it changes the slow motion of that phi, of the pendulum. And because of that fast motion, when I average over fast motion, I acquire the symmetry becomes broken of the slow motion. And this is actually exactly what is happening in the phase transitions. Any phase transitions in metal, in materials, in Higgs boson, whatever. It is this mechanism which always works. You have some slow degree of freedom, which we call order parameter in the system, and you have fast degrees of freedom, which is pretty much everything else. And if you now integrate out or average over fast degrees of freedom, that slow degrees of freedom requires that exactly this situation, and the symmetry will be broken. So that simple device which I just showed you, that Lego device, it actually illustrates one of the most important parts of the modern physics, that spontaneous symmetry. And it's actually quite amazing how close it is to a real thing. In fact, it is so close. Then this was my job talk when I was hired here. I had to give a colloquium, and that was exactly what I was talking about. Half of the hour which was given me, I was describing this this problem. Unfortunately, I didn't have the device back then. But it's so it's actually quite profound story how you average over fast degrees of freedom in order to have effective dynamics for low degrees of freedom. And if you think a little bit more about it, you'll understand that it's much more common than you can think, that you might think right now. For example, when you talk about motion of liquids, right? It's a very, very, very complicated story, right? Because liquids are made of atoms or molecules. Those molecules are moving very fast, right? But that's not what you want. When you want to describe the flow of liquid, you don't care about this molecule. All you care about is the total motion of the body of the body of liquid, right? So the flow of the liquid itself. But how do you distinguish between them? It's still a motion. If you zoom in into any particular area of the liquid, what you will see is very, very fast and very random motion. And the motion of that, the speed of those molecules is much faster than the motion of the water itself. So if you zoom in and look just in like in motion of some molecules, you will not even notice that the whole liquid is flowing, because they move so fast, right? That your total motion of the whole thing is within the error bars of your measurement of the velocity of the molecule itself. So what you need to do then, you need to average over that fast motion and say that on average they move in very, very fast, but on average they almost stay put, but still moving a little with some small velocity. And you need to capture that small velocity after averaging. You need to capture the small velocity of that molecules on the background of that very, very fast real motion. That's but that's only that separation of scales, that there is fast and slow motion, is exactly what allows us to do that. We actually know how to do that. We know how to average over fast degrees of freedom in order to find the dynamics of the slow degrees of freedom. And that's one of the examples, the simple one. But that's exactly the story how we derive hydrodynamic equations. We can derive them starting from Newton's laws, but that's exactly the procedure you need to perform. You need to average over very, very fast degrees of freedom in order to find the dynamics of low degrees. Okay? Does that make sense? So in this sense, like wind, which you feel like in your face when you like go from whatever, it's exactly that procedure. You feel the slow motion of air while there is a very, very fast motion of molecules. So your senses actually average out the fast degrees of freedom, and you feel only the slow. Okay, and it's everywhere. That makes sense?
Yes.
All right. Now finally we go to the last one, and that's when this period pretty much the same as the period of the motion of oscillation. Okay, and so now nonlinearity doesn't matter on anything. I can actually start with this one or with the pendulum and linearize it, and then say that that omega squared is that periodically depends on time, and that period is about the same. So about the same means that it can be 5 times larger, like 3 times larger. Well, the same thing. So it's not like 1,000 times. So not up orders of magnitude. So it's about the same thing. And do you know what will happen in this case? What effects we can observe? Interesting. Do you or you don't? You don't. Come on, that's only 2 answers.
I do not.
All right, good. Well, actually, you do, but you may not recognize it. It's called what's interesting there is called parametric resonance, and there is plenty of devices which use it, and so there is parametric amplifiers and electronics and so forth, and that's exactly the story which they use. So, but you know it from times when you couldn't talk, right? Because it's a swing. That's exactly the swing. So let's see that this is a swing. And again, you stand here and you bend your knee up and down. And if you remember how you do that, you stand upright here and you stand upright here. and on this point, you actually bend unique. With little phase shifts, but it's due to dissipation. But anyway, that's about how you do that. And so what it means is that you see that when pendulum goes only half of the period, right, you go full period, up, down, up. Right? So your frequency is twice the frequency of the pendulum, of the swing itself, and that's exactly the situation of this guy. Okay, so that's one thing, and so and you know what happens, right? The swing goes further and further, and you can accelerate yourself up to something. So this is that situation is called parametric resonance. Now notice that it's very different from normal resonance. Normal resonance is when you add here some force depending on time. Right. And then when that force has frequency omega, then you have a resonance condition. So for that you require external force acting on the system. Here you don't have any external force. Right. So when you stay on that pendulum, there is no external force acting on you and pendulum. So you consider the system, the total system, as you and pendulum. There is no external force except gravity, right? Which is not periodic. There is no periodic external force which acts on the oscillator, on the pendulum, right? Because everything else, when you go up and down, it's internal force for the system. And normal resonance requires external force. Normal resonance is when you have a parent staying here, right, and pushing that kid like periodically. That's normal resonance because there is external force which acts on the pendulum, right? But when you're going up and down, there is no external force. So it's a completely different phenomenon. It's not because of that of the external force. It's because of that the parameters of your oscillator, of your pendulum are changing with time, with a specific period. The mechanism of that resonance is very, very different, and the calculations is very different than with external force. It's much more complicated. In fact, the story is more complex. That's probably the most complex story on all those different things. And again, so I'm not going to derive it, but I want to nevertheless to describe what will happen. And so now what we have this equation, and we need to supply it with the boundary condition. So let's say that our initial condition at t equals 0 equals 0, and our initial velocity is also equals 0. Right? So now remember that if I had an external force here, I would still have some motion because that initial condition doesn't matter. Another person parent like comes in and pushes you, right? And so the fact that you started from zeros doesn't really prevent you from moving. But in this situation, when there is no external force, you see that there is very simple solution of this equation. Doesn't matter what omega of t, right? It's x of t equals 0. Right? So you don't move. Now, this is second order differential equation, and I have two, so it requires two arbitrary constants, and it's a linear equation, second order linear differential equation, right? It's then each solution is unique, and there is only unique solution which depends on two arbitrary constants. Those arbitrary constants are set by the initial conditions. After I set initial conditions, if I find a solution which satisfies the equation and the initial conditions, then this is the only solution which exists. Right? That's the theorem. And now you see that this is a solution. Obviously, if I substitute it here, it will solve the equation. It also satisfies the initial conditions. So this is the only solution possible in this case. Doesn't matter what you do. You can jump here, I don't know, do whatever you want. It doesn't matter. The swing will not move. And that's without dissipation, but it's there's some also. But anyway, so ideal swing would not move. So when little kid is sitting on that on that swing, right, and whining to his or her parents to start him, right? That person, that little kid already knows about the initial conditions and linearity of the equations and the theorem of uniqueness solution, right? He does. That's a strange thing, but that person has intuitive feeling of all that math, and he's right. It's impossible for him or for her to start the motion. But as soon as the parent comes in and gives a push, then my initial condition change, right? And then this is not a solution anymore because it still satisfies the equation, but it doesn't satisfy the initial conditions. So I need to look for another solution. And for that another solution, there is actually parametric resonance if it goes up and down in a good way, in a correct way. Okay, that makes sense? So you see that those little kids actually they do know about parametric resonance, but when they go to university, they apparently forget it. So what will happen then? So let me just write a little bit more precise the story in a more precise way. So let me say that this function omega squared of t, right, it equals to some constant omega naught squared, right? That's my natural frequency of my resonance, and I want to add a small addition to it. It's cosine omega p. Okay. So what it describes this function, like it's exactly what's written here, what's drawing here. It's if I have h, if this h is much smaller than 1, right? It's dimensionless because it's compared to 1. So if h is much smaller to 1, then this amplitude of change is much smaller than omega naught. And so I have, if this is much smaller than 1, I can neglect it at first, and I see that my omega squared is constant, and then it is my oscillator. Now I introduce that term is very, very small h. All right, so it's small oscillations, and those oscillations are given by the frequency of those oscillations, those changes, the frequency of the change of frequency. This omega p equals 2 pi divided by 2p, right? That controls my that exactly the frequency of change of frequency. All right. So and then what I can do then I can actually plot the following story. I can plot it like this. I can say that this is my h, right? This one, and then on this on here what I will plot it's a little bit bad notation, but nevertheless it's like this. It's the ratio of omega naught to omega p. Unfortunately, if I try to do it as omega p divided by omega naught, it would make more sense. The picture becomes very crumpled. So what will happen there is that there is some specific points, 1/2, 1, 3/2. This is the ratio of those two frequencies. And yeah. And then what I have is the following regions. Okay. And then this region is more narrow. The story is symmetric with respect to h to minus h because it really doesn't change anything. And already this one becomes very, very narrow region. Right? So the resonance, the parametric resonance exists here. So this is one half. And within those regions. They become more and more narrow. It's very difficult to observe them here. But that one is a typical one to observe. So what it tells you? It tells you the following, that resonance exists everywhere here. So if I have some particular H, some amplitude, like for example, you stay there like on a swing and you're moving yourself up and down, I can, using Taylor expansion with the delta L, right? Taylor expansion with respect to this delta L, I can find what this H is, right? And this H then is somewhere here. And if I concentrate on this resonance, then this resonance will have, I will have resonance in any range of frequencies here. So as soon as my frequency within this range around this point 1/2, and this is the ratio of the frequency, right? Then I will have resonance. And your swing will go faster and faster and faster. Right? But if you're outside, if you're not precise with your frequency, then you're outside of the resonance, and the swing will not go up and down. Will not go further and further. So it is the accuracy with which you need to keep your frequency, right? Frequency up and down. That accuracy with which you need to keep that frequency close to 1/2 depends on the amplitude. So if you have very, very, very long swing and you try to swing on it, you will have to be very precise with your frequency. Okay. That make sense? Does that make sense?
Yes.
But if you have that H a bit larger, this is all only for small H, which still this is even here it's much smaller than 1. But if you have that H a little bit more larger, then you actually have you can make a little bit, you can be a little bit less precise, right? And still have a resonance. So that's the story, and that resonance repeats itself, but that region of becomes more and more narrow. Now, but this is without dissipation. Now, if you add dissipation to the system, what happens is that instead of this sharp corner here, what you will have is something like this. I don't know. Can you see this? And the same thing here. And the same thing here. And now your resonance will exist only in this part. So again, what it means that how we analyze this is that now, when you have a small dissipation and this gap is of the order of dissipation which you have in the system, you must have that amplitude larger than some critical value. So if your swing is very rusty, you actually need to work really hard in order to get into resonance, even to get to resonance, right? So if the amplitude is smaller than some critical value, right, then you will not have a resonance. The swing will, the oscillations will decay instead of going further and further. Okay. So again, this is very, very different from normal resonance, and it's completely different story than normal resonance. What is interesting though, and of course it's very much usable. I mean, like parametric amplifiers, all that stuff, all the time. But it's actually more interesting in different way. The thing is that if you now rename a little bit of those things, especially with this then what you will get is a Schrödinger equation of electron moving in a periodic potential. That's well, I'll probably show it at some point, but for now, just trust me. So electron or quantum mechanical particle moving in periodic potential, right? Instead of time, you need to put x and then so forth. There are a bunch of renaming which you need to do and recognizing what it means. Electron moving, quantum mechanical particles moving in periodic potential is electron moving through a crystal. And then exactly the same story happens without dissipation. What happens is that electron can survive everywhere except those regions where it's classically you have resonance there. In quantum mechanics, the states do not exist. Electrons cannot exist here. And but everywhere else they just moving as if there is no crystal at all. So electrons inside in periodic potential, electrons in the crystal can move through it with no resistance whatsoever, and but they only can exist for certain specific energies. Those called energy bands, and that's exactly the same picture as this one. And this is exactly the reason why we have metals and why things can conduct, there are materials which conduct electricity because of the quantum mechanics and because of the same effect. In quantum mechanics, this is called the similar effect is called Bloch theorem, and this is basically the basis of all our understanding. That's what we start with every time we have a crystal and we want to figure out what's going on there. We start with Bloch theorem, and all right. So that's all the three regimes which I promised to show, and I was trying to tell you that it's all those regimes are very, very much connected to a lot of very interesting and sometimes very unusual physics, like this one, right? And it's also unusual in all other settings as it is here, and that's it. Any questions?
Yes, Professor. Do we need to worry about adding in dissipation for that last regime?
What do you mean worry? It depends what you want to do.
Is that something we need to worry about? Because once you did that, then it like changes it to like a hyperbola instead of just the, you know.
Okay. Well, again, so what does it mean? Do I have to worry? Well, it depends on what you're trying to do with that. Right?
I guess, is it something we're gonna have to know like for tests or like for homeworks or like something we need to?
This is parametric resonance. This is one of the most complicated stories in mechanics.
Okay.
You will never have a problem about any of this. Actually, come on, I'm not teaching you for tests. I'm just telling you interesting stuff.
Okay. Yeah. No, I just wanted to make sure.
But if you study it, it's actually a lot of fun. It's very, very interesting problem with very nice math there, very nice ideas, and the dissipation is it can be included there, and it's marvelous. And if you do that, if you want to do that, please do. There are plenty of books about it. Okay. All right. Any more questions?
So, Professor, could I clarify the axes on the graph? So I know the vertical axis is the amplitude.
I'm sorry, I don't hear you very well.
Sorry, can you hear me better now?
Just a little bit.
So I was just wondering what the x-axis is. I know the y-axis is the height.
Yes, it's not the height, it's h, that parameter.
These are the amplitude. Yeah.
This is omega naught divided by omega t. Now, in my lecture notes, this picture exists. I just drew it from my lecture. So if you go there, it's nicely written.
So I remember you called it the error just now. What did you mean by that?
You said that you need this is you said that this is what you control, right? That's how you go up and down frequency, right?
Yes.
So that's the frequency of your motion. But now it's your motion, so you cannot be precise. You always have some error bars, right? Your frequency is not precisely like, I don't know, twice the omega naught. You cannot do that. It's you will always have error bars, right? Now the question is that what error bars will be tolerated by parametric resonance, and that depends on what is amplitude of your going up and down. So if amplitude is large enough, then you can be anywhere here, right? And you still have resonance. So you don't have to be very precise. You can make that resonance will tolerate quite a bit of error in your measurement of your own frequency or your measurement of omega naught.
Okay, thank you.
For any frequency in this region, in this interval, you will still have a resonance. So you don't have to be precisely here. Now, if your h is very, very small, then you have to be very, very precise because here's your that interval is very small. You have to be very precise if your h is very small. If your h goes to 0, then the whole thing goes to the point and it's impossible. Right? So if h is non-zero, then this is very, very small region. If you increase h, then this region becomes larger and larger. So the system will tolerate your errors better and better.
Okay, thank you.
All right, anything else? All right, then, that's it. Thank you very much.